So I'm looking at both kernel of A and kernel of A minus. And of course, by simple linear algebra, you know that co-kernel of A plus is equal to isomorphic to kernel of A minus. So by looking at the kernel of A, we take into account for the operator A plus both the kernel and co-kernel. And if we are taking a trace, which is a supertrace, I'm actually subtracting something on the kernel of A by something on the co-kernel of A, and that should be related to the index of the operator A plus itself. The index of A as a self-adjoint operator is true, it's 0. So this construction, I'm actually looking at the index of the class. So the result at the end of the last lecture is that if the rank of the kernel A is constant, that means it's independent of the point in B, then this is a vector of this is also a Z2 gradient over E, and it has a induced connection. So this is a subbundle over E, and the subbundle also preserves the So that is that even though even though A kernel of A is not a bounded bundle, the determinant of kernel of A in fact is a bounded line bundle. So what is the determinant of A, kernel of A? Well, let's start with the determinant of E, the original bundle. So the original bundle is a vector bundle. It has the E plus part and E minus part. The determinant sometimes is nothing but superdeterminant. It is the determinant bundle. What is the top exterior top of E plus, and so there's the top exterior top of E minus, but there's a dual for the minus part. So this is a line model of E, and also a line model. So we are in the original bundle, so there is makes sense. So this is a bundle, line bundle over E. Now, determinant of the kernel bundle still makes sense. Well, if it makes sense, it should be defined as top exterior top of the kernel of A plus, and so this top exterior top of the kernel of A minus with the inverse. The point here is that even though the kernel is not defined, is not smoothly varying, but when kernel jumps, the kernel of A plus and kernel of A minus jump with the same amount. And here you see that one of them is without inverse, the other one is with inverse. So if they jump, the amount of jump cancel, and this is a well-defined line bundle over E. And you can see that, so what is the determinism of these models? So we divide the determinism in two forms. So we divide the determinism by times I divide it by 2 pi. So I then get the first term form. So determinism is essentially the first term form. So if I look at curvature of the original bundle, and this bundle, in the case when kernel of A is actually a bundle, because there's a connection so there is also a connection on the determinant line bundle, and you can look at this curvature of the kernel to first term form with the connection. And the difference turns out because the line bundle is essentially the curvature is essentially tracing the curvature of the original bundle. So you just connect the two-form part in the character. So connecting the two-form part, then you get dA on 1. When A on 1 is the one-form part of A. So A has an odd form. It has a 1-form, 3-form, 5-form, etc. So you just take the 1-form part, and that gives you the 2-form part of the other side. So that's the determinant line model. So you see that even if we only have a classic differential cases, it somehow gives a line, a smooth line model. Okay, so that's the finite dimensional story I want to give. So before I go to infinite dimensions, so there we go. that the dimension of fiber is even. The dimension of B, I don't think. The dimension of fiber is even. And also, this relative tangent model is spin. So that means that the structure is SO. The structure on this model is SO of whatever the even dimension is. So that SO is lifted to spin of that lambda. So in other words, there exists, because this is an even dimension, there exists the spinor model, which is the structure spinor model as an even one that is decomposing to the positive part of the negative part. So I mean, the whole model collectively of course, it implies that each fiber is spin, and when you restrict the spin model to the fiber, it is going to spin model of the fiber. And then also, I want to couple the Iran operator to physics terminology. So I also assume that there exists a condition complex E over N over the total space A. And then when we restrict ourselves to each fiber, then we have a family of these. Now this is with a convention. Also with a condition. With condition. So now I have a whole setup for you to consider a family of Iran operators. So in this case, we have a family of Iran operators. So infinite number. And the Dirac computation is regardless of the active of each fiber. So it changes the all part, given part, and all part. So you see that this is the infinite dimensional setup of what we discussed last time for finite dimensional model. So, but of course, when we carry finite dimensional solution to infinite dimensions, there will be complications. So one complication is that if you So